Hello, so today we will be discussing about the types of variables as well as the canonical and standard forms of an LPP. Okay, so let us just go ahead with this. Okay, so these are the two important variables that we will be facing. Okay, so select variable, let us just see. Okay, we will define it, maybe I will provide it in the notes. Okay, but let us see the definition. Okay, so the select variable, suppose you are having a constraint like this. If a constraint of an LPP is okay, something like this, maybe AI1 x1 plus AI2 x2 plus AIN xn less than or equal to bi. Okay, suppose if you are having a constraint that looks like this, what will happen is, suppose we want to convert this inequality, we want to convert it into an equality. What will we do? Surely because it is less than, so we will have to add something, right? That's something that we will add. Okay, it will be a variable which is called as the select variable. Okay, so if you are having one constraint that looks like this, you will be having one select variable. Similarly, if you are having two constraints, maybe you are having another constraint over here, and then you can have two select variables, or you can have three, okay, depending on the number of constraints that look like this. Okay, then we can convert the above constraint into an equality by adding in a variable called as a select variable. Okay, so the new constraint will look like this. Plus AIN xn, because you are adding one select variable and it is with respect to the row AI. Okay, so maybe you will get S1. Okay, let us just denote it with S1. Okay, if you want to be more particular, maybe S1i. Okay, but we really don't need that. Okay, maybe we can just write the as S1. So you add this one and it will be equal to bi. So S1 will be a select variable. Then S1, it will be non-negative, is a select variable. Okay, so this is what happens. Okay, select variables, they are used when the inequality it is less than or equal to. Okay, but what happens if the inequality is greater or equal to? Do not worry, we will do examples. Surplus, okay, surplus variable. Okay, if the constraint of an LPP is like this. Okay, so you want to convert it into an equality because it is greater than. So if you have to make it equal, you will have to subtract something over here. Then we can convert the above constraint into an equality by subtracting a variable called as a surplus variable. Okay, so we can just subtract over here. Still, okay, we can just denote it with S1, it won't matter. Okay, minus S1 equal P1, then S1 is a select variable or surplus. Again, I repeat, surplus variables, we are having the greater or equal sign and we are subtracting. Okay, and also sometimes you will be having that there will be variables of unrestricted sign. Okay, variables. Okay, so whenever we say it is unrestricted sign, okay, just remember this, okay, because when we are doing LPP, if you remember that the sign restriction was x1, x2, x3, all of them have to be greater or equal to 0. That is, they have to be non-negative. They should not be negative. Okay, but what happens if we have something like this, variable of unrestricted sign? That is, they can be positive as well as they can be negative. So whenever you see this word, then if x, okay, maybe if xi is a variable of unrestricted sign, then xi, okay, maybe xj can be written as, okay, it can be written as okay, xj, we can write it as xj dash minus xj double dash, okay, where xj dash and xj double dash greater or equal to 0. Okay, this one, the logic, it follows like this. Suppose if you are having the number 9, so 9, it is positive, you can write it as 9 minus 0. Okay, where 9 is greater or equal to 0 and 0 is greater or equal to 0. Okay, so we can write it like this. And even if you are having a negative number, say minus 9, still you can write it as, okay, 0 minus 9. Okay, where 0 is greater or equal to 0, or you can even write this one in another way, maybe 1 minus 10. Okay, you can even write this one as 2 minus 11. Okay, so we can write it in so many ways, but the main thing is that we can express it in terms of two variables, the difference, and both of them should be greater or equal to 0. Okay, with this being said, okay, now let us take a look at the two different forms of an LPP. Canonical form. Again, I will provide the notes, do not worry, and standard form. Okay, so I'm writing it in this way so that you will see the difference. Okay, so over here, what we will do in canonical form is we will always have a maximization problem. We can always convert a minimization problem into a maximization problem. Okay, you will see. Okay, so it will always be of this form, maximize z, or it can be anything as long as it is maximized. Okay, again, this z is just a notation, it can be anything. Okay, so we will be having a maximization problem, c2x2, okay, plus cnxn. And then the constraint will be of this form. Okay, it will be ax less than or equal to b, where x I is greater or equal to 0. Okay, so we always have to, if we have to use canonical form, we always have to write it in this way. Okay, if you want to write, where A, it is the matrix Aij, m cross n. B, the vector B, B, it is this vector B1, B2 up to Bm, and X, it is the vector X1, X2 up to Xn. Okay, so we have to always write it in this way. Okay, the main thing is this one should be less than or equal to. Whereas for a standard form, again, it should always be a maximization problem. Okay, I will provide the notes. Cnxn. Okay, so we are having something like this. Okay, but the constraints instead of a less than or equal sign, it should be equal to b. Xi should be greater or equal to 0. And over here we have another restriction, is that they should be non-negative. Okay, and also the vector b should be greater or equal to 0. Okay, that is b1, b2 up to bm. This should all be greater than 0. Okay, so this is basically the standard form. Okay, the main thing over here should be equal and it should be positive. Over here we don't have such restriction on the vector b. Okay, over here I am saying vector, but I'm written in terms of matrices. Always remember this. Okay, whenever we are writing a vector like this, as you have learned when you were doing linear algebra, so this one is a vector, we can write it like this. When you are writing it like this, just remember that we should be using the column vector. Okay, so we can write on this one as something like this. Okay, if we want to use, if we have to denote, okay, do not denote this one with this vector. Some of you may make a mistake. Okay, some of you may be representing this vector with this row matrix, but that is not the case. Whenever you represent this vector, represent it with a column matrix. Okay, so this is basically about the canonical form and the standard form. Okay, so now let us just do some exercises so that it will be clear. So now we will see how to convert an LPP into standard form, but first we must need to know how will we convert a minimization problem into a maximization problem. Okay, we can do that by just using this very important relation, minimize z equal minus maximize minus z. Okay, so this one is very important if you have to convert a minimization problem into a maximization problem. Okay, so with this being said, let us just look at the examples. Okay, so convert into standard form. The LPP is this. Okay, minimize z equal minus x1 plus 3x2 minus x3. Okay, subject to, I will write it over here, x1 plus x2 plus x3. Okay, I'm just making up these constraints. It can be minus less than or equal to 6. Okay, the other one is 3x1 minus x2 minus 5x3 greater or equal to minus 5. Okay, less than or equal, let's see. Okay, another one is 5x1 plus x2 plus 3x2 maybe minus 5x3 greater or equal to minus 6. Okay, and then another one is 6x1 minus 7x2 minus 7x3 greater or equal to 7. Okay, and then we are having these two things, x1 greater or equal to 0, x2 greater or equal to 0, whereas x3 is unrestricted. Okay, so what we will write, the solution will begin like this. Solution, since x3 is unrestricted, so because it is unrestricted, we have learned that we can write x3, we can write it as x3 dash minus x3 double dash, where okay, x3 dash and x3 double dash are all greater than 0. Okay, so what can we do? Now we have to convert this one into a maximization problem. So the LPP is, okay, so we need to convert this one into a maximization problem. So we can just write it down as max z star. Okay, once you write this one, you will change the signs. So the signs will change into x1 minus 3x2 plus x3. Okay, we are changing the signs because of that relation that I had given. Okay, but x3, it can be written as x3 dash minus x3 double dash. Okay, and then just leave some space over here as well. Okay, maybe I will write it to the left side. Okay, max z star is equal to this x3 dash minus x3 double dash. Okay, and then just leave some space. Okay, you will see why. Okay, but for now, just leave some space over here. Okay, so now what we will do, we will convert this one into an equality. Okay, and over here you should also remember this line, z star, it's equal to minus z subject to the constraints. So we need to convert this one into an equality. Okay, let us first look at this one. Okay, so over here you must also remember that on the right side of the equality it should be positive. This one is already positive, so we don't need to do anything. So we can just write it down as 3x1 minus x2. Instead of x3, we have to put in these new variables, x3 dash minus x3 double dash according to this relation. But also we want to convert it into an equality, so we can just write plus s1, okay, by using the slack variable s1. So we can convert it into 6. Okay, so I hope that is clear. Okay, so this is the first constraint. Okay, do not worry, we will mention what are s1, s2 later on. Okay, so this one is done. So now what we will do, we will convert this one into an equality as well. But first we must get rid of this negative sign. Okay, if you get rid of this negative sign, you will be having minus 3x1. You can multiply both sides by minus, plus x2. Okay, I'm just showing the steps, then I will write the answer directly over here. Plus x2, this one is 5. Okay, minus, it will be converted into a plus 5. But then x3, it is x3 dash minus x3 double dash minus 5 x3 double dash. We have multiplied it with greater or equal to 5. We have multiplied it with minus, so the inequality also changes. So ultimately, if we have to convert this one into an equality, we have to subtract a surplus variable. So this one will change into minus 3x1 minus x2 plus 5x3 dash minus 5x3 double dash. We have to subtract another variable, which is a slack variable, equal to 5. So this is how we do it. Okay, so this one is also done. Okay, I will write the answer on top now. Okay, this is the answer, this is the explanation. Okay, so now let us take a look at this constraint, 5x1. Okay, so this one is negative. We first have to convert it into a positive. Okay, so positive, we can multiply both sides by minus 5x1 minus 3x2 plus 5x3. This one will be converted to less than or equal to sign, and over here we will be having plus 6. Because it is less than, so we have to add something. That is why, continuing from over here, we will be having minus 5x1 minus 3x2. But again, x3, it can be written as x3 dash minus x3 double dash. So we'll be having 5x3 dash minus 5x3 double dash. We have to add another variable over here, which is a slack variable, s3 equal to 6. So this is how we do it. Okay, so this is also done. Now we just have to take care of this one. This is already positive, so we just have to need to subtract a variable over here. So we'll be having 6x1 minus 7x2 minus 7x3, but this one is negative sign, so it will be minus 7x3 dash plus 7x3 double dash. Now we need to subtract a variable which is a surplus variable because of this inequality, equal 7. Okay, so this is done. Okay, now all the variables, now if you are seeing the variables, they are x1, x2, x3 dash, x3 double dash, s1, s2, s3, s4. Okay, so we can write it as x1, x2, x3 dash, x3 double dash. Now we are having so many variables, s1, s2, s3, s4, they are all greater than 0. We can just mention s1 and s3 as slack variables. S2 and s4, they are surplus variables. Okay, so this is how we do it. Okay, but if you remember, I said that you must leave some space over here. Why should you leave some space? Because now the objective function should also contain as many variables. We can do that. Okay, so s1 is not present in this original objective function, but we can do that. We can just write 0s1 plus 0s2 plus 0s3 plus 0s4. Okay, so this is how we do it. Okay, I hope it is clear. So this is a very easy question. Okay, if you have to convert something into a standard form, it's very easy. You must remember, however, that if it is already a maximization problem, then keep it as it is. Okay, maybe I will do another question. Convert into canonical form. Okay, so this one, what I will do over here, it's already a maximization problem. Okay, if it is minimization, you can change it into maximization just by following the steps by using Z star, take the negative. Okay, but let's see. 7x3 subject to x1 plus x2 plus x3 greater than minus 7, x1 minus x2 plus x3 less than 6. Okay, and also x1 minus x2 plus 11x3 less than minus 6. Over here we are having x1 is unrestricted, x2 greater than 0, and x3 is also unrestricted. Okay, because it is already maximization problem, so we will keep it as it is. So the LPP in standard form is in canonical form. The LPP in canonical form is Okay, actually the solution you should start over here. Since x1 is unrestricted, therefore x1 is equal to x1 dash minus x1 double dash. Similarly, since x3 is unrestricted, also x3 we can write it as x3 dash minus x3 double dash. Okay, x1 dash, x1 double dash, x3 dash and x3 double dash, they are all greater or equal to 0. So this is what we are having. So now we just need to convert this objective function. So instead of x1, we will write x1 dash minus 2 x1 double dash plus x2. x2 it's already greater than or equal to 0, and minus 7x3 minus 7 x3 dash plus 7 x3 double dash. Okay, subject to. So if you remember canonical form, we just need to convert this one into less than. Okay, everything should be less than or equal to. Okay, standard form we are converting it to an equality, but canonical form it should be less than or equal to. Okay, to convert this one to a less than or equal to sign, we can just multiply both sides by minus. Okay, maybe I will also change the question. Okay, just change the question, make it greater or equal to 6. Okay, actually we will see why. Okay, so we can just convert it to minus. So the answer will be this: minus x1 minus x2 minus x3 less than or equal to 7. So this is what we are having. Okay, after multiplying by minus, and over here we are having and also remember x3 x1 you can write it as x1 dash minus, okay, so sorry, so it will be minus x1, so it will be minus x1 dash plus x1 double dash plus x2 minus x2, it will be minus x3 will be minus x3 dash plus x3 double dash less than or equal to 7. So this is what we are having. Next, okay, this constraint it's already less than or equal to sign, so we don't have to multiply by minus. Okay, so you will see you will be having x1 it's x1 dash minus x1 double dash minus x2, it stays as it is, x3 it will be x3 dash minus x3 double dash less than or equal to 6. Okay, so this takes care of this constraint, and this one it is greater or equal to, so we still have to multiply it with minus. Okay, if we multiply with minus, you will be having minus 7, okay, x1 dash plus 7 x1 double dash minus x2, sorry, will be plus x2, then will be minus 11 x3 dash plus 11 x3 double dash less than or equal to minus 6. Okay, in canonical form we can have negative values here as well. It doesn't really matter. In standard form you only need positive values over here. Canonical form it doesn't matter, we can leave it as a negative sign. Okay, so the only thing now we should write is x1 dash, x1 double dash, x2, all the variables that are over here, they are all greater or equal to 0. So this is the required solution. Okay, the LPP in canonical form is this. Okay, it's very easy. Until next time.